to pages 2, 3, and 4, and I'd like you to complete the next 3 columns on pages 2, 3, and 4. For example, I drew the Lewis structure here for HCl. Whenever there's only 2 elements, there is no central atom. Okay, when you have a diatomic molecule, and a molecule composed of 2 atoms, there is no central atom. The geometric shape immediately is linear because 2 atoms can only be separated by 180 degrees. Again, Cl2 is also got 2 atoms. It too can only be linear. So you just cross off, whenever you have a diatomic molecule, you cross off those middle sections. And the geometric shape is linear, which means the bond angle between H and Cl is 180 degrees. If you have ionic compounds, NaCl is an ionic compound. For any one that you labeled ionic, you do not have to do this for, because this is molecular geometries. We are only doing this for molecules. Ionic compounds, I'm simply just going to ask you to be able to draw a Lewis structure. It's what you did in the last test. The test in this class is going to focus on molecules and not on ionic structures. Okay? OF2, I forgot the lone pairs here. So now, how many atoms are coming off of the O? Now we have 3 atoms. Once we have 3 or more atoms, we're going to have a central atom. So the O is the central atom. How many atoms are coming off of it? 2. There are 2 fluorines coming off of it. How many lone pairs does it have? 2. So this would be an AB2E2 molecule. So if I need to, I can go back to my chart and find wherever I have an AB2E2. And whenever you have this scenario, the molecule is said to have a bent geometry. The geometric shape is bent. NH3. 3 atoms are coming off of it. 3 H's. It has 1 lone pair. So this is an AB3E1. Again, this would be my B, and this would be my E. So I have an AB3E1, or E. This is called trigonal pyramidal. It's a triangular base pyramid. So this is all I want you to do now for the rest of these molecules is complete. All you got to do is put in a number, or if it's an ionic structure, cross it off, and put down what geometric shape each of these have. Your homework is to go back. Okay, again, these you should have filled out already, so you're going to now do the number of atoms and geometric structure. Be careful, any of them that are bolded, there's more than 1 central atom, so you're going to have to do, like I just showed you with that X, Y, and Z molecule, where you have to look at each central atom individually because they might have different geometric shapes. Now we're finished doing those 3 columns. I will place the answer key to these online on Friday, and you can check your work over to see how well you did on getting these geometric shapes of these molecules. All right? If you have any questions, please contact me, but hopefully now you got a good idea of geometric shapes. And if not, when you come to class, be ready to ask me questions, and I'll be glad to go over some examples with you in the next couple weeks so you get really good at this geometric shape information. All right, today's lecture is going to look at investigating what's called molecular geometries. Molecular geometries is looking at what geometric shape and angle there are that results between adjacent atoms that are coming off the central atom. And the rule of thumb is when we have atoms that are bonding off of another atom, these electrons that I'm circling here in the bond, they want to be as far apart as possible because we want to minimize the electron repulsion. Electrons repulse other electrons. So we want to get these bonds and these electrons as far away from each other as possible to minimize the repulsion, and that will give the shape of the molecule its most stable configuration. This concept or this theory is called VSEPR. VSEPR stands for valence shell electron pair repulsion. In essence, it's just what we talked about. Let's get these valence electrons as far away from each other as possible, and what geometric shape results from that. And this is where some of your geometry that you're taking or have taken will be very helpful in this course. One other thing I'm going to do is when I start creating these molecules, I'm going to create what's called a type of molecule that's dictated by these A's, B's, and E's. And A is the central atom. Who's in the middle of the molecule? B is the adjacent atoms, the atoms that are coming off of the central atom. And E is the lone pairs of electrons, the double dots that are surrounding the central atom. So for example, in the structure that I gave you with X here, maybe X has got a double dot in one of the corners. That would be called a lone pair. It would have one lone pair, and there would be 3 atoms coming off of it. Okay, so this would be a molecule that would be said to be an AB3E. Okay, it has one central atom, which is X. It has 3 bonds coming off of it. 3 atoms are bonded off of it, B3, and it has one lone pair for E. In essence, you could also say E1, but really that's not necessary there. So an AB3E is the type of molecule this would be. So any molecule that has 3 elements coming off of it and has one lone pair will have the same molecular geometry as any other compound that has that same exact bond type. Okay? All right, so let's start drawing these. Now, in order to do the VSEPR structure, or the 3D structure, we have to first do the 2D structure. The 2D structure is a Lewis structure. It's what you did in the last lecture. So the first thing we're going to do is draw the 2D structure of Cl2. I jumped ahead of myself. Chlorine has got 7 valence electrons. It has 1 single dot, and therefore you'd predict it wants a bond once. So if we have another chlorine atom, the 2 single dots face each other, we connect the dots, and right there is the Lewis structure for this molecule. Now, what comes next is the 3D structure. The 3D structure is the VSEPR structure. What does it look like in real life? When you come to class this week or next week, you're going to be working with a molecular model kit. The molecular model kit allows you to see what the molecule looks like in 3 dimensions, what it looks like in real life. The Lewis structure is not an accurate depiction of it. If you only have 2 atoms, it's like in your geometry class where your teacher said if you have 2 points, no matter how they occur in 3-dimensional space, you can always connect them with a straight line. So 2 atoms can only be separated by 180 degrees. And therefore, whenever you have 2 atoms, the VSEPR structure looks exactly like the Lewis structure. There is no difference. Okay? The geometry, the molecular geometry, this molecule is said to be a linear molecule. Linear means that the bond angle, the atom to atom, the bond angle that results is 180 degrees. So sometimes they'll also talk about the bond angle that results, or what is the separation of the 2 atoms from each other. And that bond angle, whenever it's linear, is 180 degrees. It's the greatest bond angle separation you can have in 3-dimensional space. And then the type of molecule that this is what's called an A2. There technically is no central atom. There is no adjacent atoms. They are both the same element bonded to itself. So A2, whenever there is no B or adjacent atoms coming off of it, anything that has an atom bonded to itself is an A2, which means it's a linear molecule. 2 atoms can only ever be 180 degrees separated. Okay? So anything that is a diatomic molecule, any molecule containing only 2 atoms, regardless if it's the same atom bonded to itself or different atoms bonded to itself, will always be 180 degrees and be a linear molecule. Okay, let's look at drawing the next molecule, HCN. Now, I'm going to draw it immediately to try to keep this lecture as short as possible, but please pause the lecture if you want to before you begin the next one, just so you can see if you can get the Lewis structure correct before I draw it. The carbon will form 3 bonds with the nitrogen, forming a triple bond, and a single bond to the other hydrogen. Right there is the molecule HCN. Its 3D structure, again, what is the best angle we can do to separate the H and the end? And again, when there's only 2 elements coming. Now here we do see a central atom. Carbon is the central atom. But the best bond angle that results between 2 atoms is still 180 degrees. So this is still a linear molecule. And therefore, since it's linear, the VSEPR structure is drawn exactly the same as the Lewis structure. The type of bond now, this would be, or the type of molecule would be an AB2. Okay, there's a central atom, which is the carbon, and it's got two atoms coming off it. The type of bond, if it's a triple or single, doesn't make a difference. It's how many adjacent atoms are coming off the central. In this case, there's a nitrogen and a hydrogen coming off, which is an AB2. There are no lone pairs of electrons. Again, if you look up here for E, it would be lone pairs of electrons on the central atom. There are no double dots on the C, so there is no E that pops up as the type. So any molecule that's an AB2 will be a linear molecule. All right, next one, BH3. Go ahead, pause the lecture and draw the Lewis structure. Boron's got 3 valence electrons. Boron, as we saw in the last lecture, is hypovalent. It will not meet the octet rule because it can only form 3 bonds. Now, whenever we get beyond 2 atoms coming off, now we have 3 atoms coming off, this is a AB3. Whenever we have 3 or more atoms coming off, the 2D structure is not what it looks like in real life. What's the best bond angle we can do to separate these hydrogens? Right now, the bond angle looks like it's 90 degrees. But that's because in a Lewis structure, we are always drawing atoms in the X and Y plane in 2 dimensions. And 90 degrees is the best that we can do. But in 3 dimensions, we had the Z plane, so we can do better than that. In real life, the best bond angle ends up being, if you think of a pie, and you were to cut that pie into 3 equal pieces, each angle, each of these hydrogens are separated from each other by 120 degrees. So the best bond angle that we can get when we have 3 atoms coming off a central atom is 120 degrees. It's like cutting a pie into 3 pieces. Now, this molecule is still flat. It exists only in 2 planes. It still exists only in the X and Y plane, but we are not looking at being at right angles, which is what a Lewis structure is when we draw it. The geometric shape for this, and this is where you're going to have to do a little bit of memorization, this is called trignoplanar. It's trigonoplanar or trignoplanar, however you want to say it, like potato, potato. Trigonoplanar means that we are forming a triangle. Planar means that it's flat. It's creating a flat triangle. It exists like it's a sheet of paper, X and Y planes. Just like a piece of pie is it's a flat molecule in essence there too. So with that, when you cut a pie into 3 equal pieces, you're going to get 120 degrees. So the geometric shape, this is called trigonoplanar. All right, CH4, moving on, building on. Carbon has got 4 valence electrons, 4 hydrogens. The Lewis structure looks like it predicts, again, 90 degrees. But we find out when we draw this molecule using a molecular model kit that 90 degrees is not the bond angle. It gets much bigger than this. And now this bond type is called an AB4. Again, there's no double dots, there's no valence there's no lone pairs of electrons, but there are 4 atoms coming off the central atom. This is an AB4 molecule. When we draw the molecule, we use what's called the dash and wedge method. One hydrogen comes directly off the top. The bond angle that is found is not 90, but it's actually greater than that. It's obtuse. The bond angle that results between the 2 adjacent hydrogens is actually 109.5 degrees. And that is found to be true for all of the geometric shapes. So now there's another hydrogen at 109.5 degrees, and this guy, what's weird about it is it's coming out towards us. It's coming out of the board between your flat iPad screen and your face. It's coming out towards you. And this is what the wedge is designed to show. The wedge is just designed to show that the hydrogen's coming towards you. And there's another hydrogen that's going behind the back of the iPad. This is called the dash and wedge method. Okay. Now, if I were to connect all of these, what I literally create is a triangular base pyramid where the hydrogens are each of these corners, and the carbon is in the middle. We're in essence creating almost like a diamond shape in which the carbon's in the middle, but all these bonds, again, here's the hydrogen coming out towards you, this is one going behind the board, and these are the two that are flat with the board. This is what it's drawn. So if I were to kind of add a new color into here, just so you can kind of see it again, here would be one plane, here would be another plane, there'd be a plane behind the board, and then there's a plane in the bottom. We're creating this triangular based pyramid. And I'm sure in geometry you talked about triangular based pyramids, and that's exactly what this shape attains. And every single angle, no matter what two hydrogens you're looking at, all of them are 109.5 degrees. Every single one. So no matter how you move and turn this pyramid, it always looks exactly the same. The name of this shape is said to be tetrahedral. Tetra means four, hedral means sided. This literally means four-sided because we have four planes, okay? And I've drew all of them. One plane, two planes, back, three planes, bottom plane, four. It's four-sided. They're four equal sides. This is tetrahedral. So any molecule that's an AB4, where you have four atoms coming off of the central, and there's no lone pairs of electrons in the central, this is a tetrahedral structure with a 109.5 degree bond angle. Okay, let's turn the page. Those four areas of electron density can be four bonds, except BH3. Trigonoplanar, this is a molecule that can be hypovalent. Now, there sometimes can be trigonoplanar molecules that follow the octet rule, but typically, a lot of times, if it includes boron, it will be hypovalent. To this molecule here, number 3, BH3, where the bond angle is 120. Tetrahedral, trigonoplanar, and linear. There are 7 geometric shapes. Those are the 7 shapes. So when you do the test for this unit, you are going to be expected to be able to name what geometric shape surrounds a central atom, and these bond types here will help indicate or be able to match up what geometric shape that it is. Okay? Now, this is all. AB4 is found when we have tetrahedral. Water, H2O. Let's draw the Lewis structure. We've already drawn this Lewis structure in the past lecture. Oxygen's got 6 valence electrons, so we predict it wants to bond twice, which it does. Here's the Lewis structure. Now, what happens when we do the 3D Vesper structure? The lone pairs occupy electron density just like the bonds do. So we treat a lone pair just like a bond. The lone pair or the bond, these are called electron domains. A domain just means a position or location of. We have 4 locations of electron density to place around the oxygen. So we place the double dots and treat them as if they're just a bond. We would treat this just like the last molecule we drew with oxygen. With carbon with CH4. So I put the top double dots on the top, and I tend to lobe them. This is what we typically do in chemistry, just to show that they take up space. The next lobe of electrons comes out at you, and the separation between these is 109.5 degrees. We have the hydrogen that's wedging out towards you, and the hydrogen going back behind you. Okay, again, the hydrogens are separated by 109.5 degrees, just like everything else. There's 109.5 degrees between the lone pairs of electrons and the hydrogens. This too, if you were to connect all these faces, one side, 2 sides, back side, 3, and then the bottom 4. Okay. Now, we do not call this geometric shape tetrahedral because tetrahedral implies that all 4 sides are the same. And here, 2 of the sides have got lone pairs attached to it. The word that we use to describe this is we say this is a bent molecule. Because when I draw water molecularly, it looks like this. the hydrogens and the oxygens literally make it look like it is a V. The oxygen being here and the hydrogens being here. This, in essence, looks like it's a bent line. And so we call this molecule bent. The bond angle is still 109.5 degrees. So a structure that is bent has the same bond angle as if it's tetrahedral. And lastly, the type of molecule this is an AB2E2. This is an AB2E2 because the two hydrogens coming off make it B2, and oxygen has got two lone pairs, which makes it E2. And so AB2E2 is the type of molecule this is. Okay? Now the nice thing is this lecture, I'm showing you all the types. When you do the homework problems, every single molecule you draw will be one of these shapes that I've drawn here. You just got to be able to match it up. If you're able to identify the type of molecule it is, you can come back to this lecture and identify what type of geometric shape it is. All right, NF3. Nitrogen's got 5 valence electrons. We would predict that it wants to bond 3 times. We have 3 fluorines. Each fluorine wants to bond once to fulfill the octet rule. And right here is the molecule NF3. Again, we have 3 bonds and we have a lone pair. So just like water and just like CH4, there are 4 areas of electron density. Again, we are going to draw this shape utilizing a tetrahedral start. So now we have the lone pair that's off the top, and I just tend to lobe it. You wouldn't have to do that, but that's how I do it. There's one at 109.5 degrees from that. There's the one that's coming out towards you. Oops, it's not H, it's F. And again, don't forget to include the lone pairs off the F. Now, they don't do anything for the geometric shape, but without having those dots on the fluorines, we do not have a correct Lewis structure because it does not show all valence electrons, even if those electrons don't count towards the geometric shape of the molecule. And then there's the F that's going out behind the board. This would be the 3-dimensional structure. Now, to name the structure again, the lone pair of electrons does not count. So if I look at what's left, it literally looks like it too almost looks like it's a triangular-based pyramid. The nitrogen is not in the same plane as the fluorines. It's actually pulled up due to the lone pair of electrons. Okay? And because of that, this is not trigonal planar. This is called trigonal pyramidal. Because it forms, the nitrogen is pulled up to form the 109.5 degrees, and therefore it is not a flat molecule. When you make this molecule in class, you're literally going to see the nitrogen above the fluorines. The fluorines are the base, and the nitrogen is above, creating a pyramid shape. This is called trigonal pyramidal because it's a triangular-based pyramid. The type molecule this is an AB3E1, or just AB3E. It's got 3 atoms coming off of it, and it's got 1 lone pair. And again, the lone pair that the E is critical for is how many lone pairs of electrons are on the central atom. In this case, nitrogen has only 1 lone pair, so it's an E. The bond angle is still 109.5 degrees. So 109.5 degrees is the most common bond angle that you're going to see, and this happens whenever there are 4 areas of electron density. Or it can be 2 bonds and 2 lone pairs, or it can be 3 bonds and 1 lone pair. If you have 4 places of electron density, you're going to have 109.5 degree geometry. Now, so far, every single shape that I have drawn has followed the octet rule. 7 and 8, the last two, 7 and 8, can only occur if it is hypervalent. So we can only get these last 2 shapes if we have more than 8 valence electrons that surrounds them. And these are the last 2 shapes you need to know for this unit and this exam. PCl5, phosphorus, has got 5 valence electrons. It would typically bond 3 times if it were to form a Lewis structure that follows the octet rule. But since it is hypervalent and since there's 5 chlorines, each of these locations will form a bond with chlorine. And right there is the Lewis structure for PCl5. If I count around the phosphorus, it has 5 bonds. There are 10 electrons that surround phosphorus. As I told you in the last lecture, when a molecule becomes hypervalent, it will either have 10 electrons around it or 12. All right, how do we draw this molecule in 3-dimensional space? The phosphorus goes in the middle, and the first 3 chlorines will create a pi. So think of a circular pie in which each of the chlorines, I'm cutting that pie into equal pieces. I go back degrees. So these are separated by 120 degrees. All of these are separated by 120 degrees. It's cutting a pie into equal pieces. But then we have a chlorine that sits on top of the phosphorus and one that sits out of the bottom. So it's like having a skewer, a bamboo skewer or a stick that pokes right through the center of the pie, in which we have a piece of the stick above it and below it. And this now creates a 90-degree angle. So this chlorine to this chlorine is 90 degrees. This is said to be, okay, the name of this molecule is said to be trigonal bipyramidal. Bi meaning two pyramids. If I look at this, I've got a triangular base pyramid with the 1 chlorine to the 3 chlorines in the disk, but then I have another one on the bottom. So it's like I have, in essence, a diamond shape. I have 2 triangular base pyramids butt to butt, creating this diamond-shaped configuration. And this is why we call it trigonal bipyramidal, is because it's 2 triangle-based pyramids butt to butt. Okay? This is called an AB5 molecule. There's a central atom which has 5 atoms coming off of it. And the bond angle, which is odd, this is the only time you're going to see this. It has both 120 degrees and it has 90 degrees. It has 2 bond angles. The chlorines within the disk are separated by 120 degrees, and the chlorine on top and bottom form 90 degrees to each of the 3 chlorines in the inside of the disk. Okay? Lastly, SF6. Sulfur has got 6 valence electrons. We would predict that it would bond 2 times. And it does bond twice when it follows the octet rule. But now it's going to bond 6 times. Each valence electron will form a bond. Again, each fluorine has 3 lone pairs, which we do need to include if we want to be complete and get full credit. So right there is the Lewis structure. How do I draw the VSEPR structure? Again, now I create this disk in between, but instead of having 3 elements in the disk, now there are 4. So it's like having a flat piece of paper. So I have a plane of paper where I have, in essence, the sulfur is in the middle of the paper, and the fluorine is, or are, the 4 corners of the piece of paper. So here's my piece of paper. It would be a flat piece of paper with sulfur sitting in the middle. But then we have a fluorine that comes right off the top and one that comes right off the bottom. Now, the nice thing about this structure is any fluorines that I look at with each other, no matter which ones I look at, everything is 90 degrees. Every bond angle here is 90 degrees because it's 90 degrees in the disk and it's 90 degrees to the disk. So the bond angle, every bond angle is 90 degrees. This molecule is called an AB6 because it has 6 atoms coming off of it. And this is called an octahedral. Octa meaning 8. This means 8 equal sides. This is an 8-sided structure because, again, if I were to take my color here, I create now not a triangular base pyramid, but now I create a square pyramid. I've got a square pyramid that the fluorine on top forms a configuration with, and a square one on the bottom. I have 2 square pyramids put butt to butt, but in essence there are 4 sides on top and there are 4 sides on the bottom. Again, it looks like it's a diamond shape, but now it's got 4 points of contact around the equator, and each side is equal, so it's an 8-sided structure, octahedral. So those are the names of all your geometric shapes. We have octahedral, trigonal bipyramidal or trigonal bipyramidal, trigonal pyramidal, bent, and good when you only have one central atom. Some of the molecules you drew in the last lecture have more than one central atom. Let's say this is the molecule that you draw. How many central atoms do you see here? Now, a central atom would be an atom that has more than 2 elements coming off of it. So who is central here? Who has more than one atom coming off of it? I'm hoping you see 3. X has got 4 atoms coming off of it. Y has got 2 atoms coming off of it, X and Z. And Z has got 3 atoms coming off it. The oxygen, the hydrogens, only have 1 atom coming off of it, so they are not a central atom. So you might be asked on the test, I might draw the molecule and draw an arrow and say, what is the central or geometry around the X atom? So now when you have a molecule that is bigger than one central molecule, you have to look at each atom case by case. Well, if I look at X, X has got 4 atoms coming off of it, and it has 0 lone pairs. Therefore, it would be an AB4 molecule. If I look back, so the X would have tetrahedral geometry, and the bond angle would be 109.5 degrees. X has tetrahedral geometry because it has 4 atoms coming off of it, and it has no lone pairs. Go ahead and see if you can now pause the lecture and do Y and Z, and see if you can identify it. So now if I were to ask you to give me the type of geometry on the Y, you'd be able to indicate what that would be. Or if I point to the Z, what geometric shape surrounds the Z. Okay, in Y, we have 2 atoms coming off of it, X and Z, and it also has 2 lone pairs. Therefore, it is an AB2E2. Now, the central atom, the A, would be Y. In each case, we make the central atom be whoever we want it to be. Y has got 2 atoms and 2 lone pairs. It's an AB2E2. And what do we call that geometric shape? That is bent. And therefore, it has 109.5 degrees. X and Z would be separated by 109.5 degrees based on the fact that it is bent because it's an AB2E2 around the central atom Y. Z has got 3 atoms coming off of it, Y, H, and O, and it has 0 lone pairs. So this would be an AB3. If a bond is a double or triple, that does not do anything different or unique to the geometry. The only questions you're asking yourself are how many atoms are coming off of the Z. Y, H, and O are coming off of Z. So it has 3 atoms coming off of it, and there's no double dots on it. This is an AB3 molecule. Whenever it's AB3, if you look back at the shapes, this is called trigonal planar. It's a trigonal planar molecule, and it has 120 degrees. So the H and the O would be separated by 120 degrees. The X and Z would be separated by 109.5 degrees. And the H's would be separated by 109.5 degrees. So we can see that these bond angles are vastly different than what the Lewis structure would show. The Lewis structure shows everything at 180 or 90 degrees. That is further from the truth. So I wanted to show again that this is an honors class, so taking to the next level. In regulars, we'd probably just show molecules with one central atom. But in your homework for today, you're going to see where there's multiple central atoms. And now can you identify what they look like? Okay?